Okay, good afternoon. My name is Kostas Vournas. I'm a professor emeritus at National Technical University of Athens in Greece, and I'll be happy to co-chair this session on power system dynamics, second session on power system dynamics, together with Robin Preece from the University of Manchester. And we'll share the presentations, the chairman's work. Robin will introduce the speakers during the presentations, and I will chair the panel session. So the first paper is from the University of Manchester, but it will be a recorded presentation by Ms. Yitian Dai, while Robin will be here to take care of any questions that may arise during the presentation and also during the panel discussion. So, Robin, the floor is to you.
Thank you very much. Yeah, this is another tale of visas that didn't quite come through in time. So Yitian was very keen to be here to present this work and has prepared this video to make sure that I don't mess it up. So we'll play that, and then I'll do my best to answer any questions that you've got.
Hello everyone, my name is Yitian Dai from the University of Manchester. I'm going to show you our recent work about the benefit and challenges of dynamic modeling of cascading failures in power systems. In my presentation, I'm going to show you firstly, what am I looking at? What is cascading failure and why do we have to study it now? Details about model development as well as the challenges and possible solutions will be presented. After that, case studies will show how the internal parameters affect the simulation efficiency and result accuracy. The main findings will be discussed. Power system blackouts are low probability but high impact events. Understanding their common features can help prevent future blackouts that might be initialized by a similar reason. Well, let's look at a recent blackout in the UK and in Texas. The 2019 UK blackout was triggered by two almost simultaneously power plant losses. The technical report highlighted the need to review the communication process, the under-frequency load shedding scheme, and also the protection settings. The Texas blackout last year was an extreme weather-related event. An extreme winter storm caused massive generator outages in the state of Texas. Timeline of frequency on that day showed a significant frequency drop caused by generator outages. This then triggered the load shedding scheme in order to avoid system collapse. Extreme weather is a rare event, but a system-wide risk assessment of climate-related threats would help improve system resilience to unexpected situations. Cascading failures are recognized as the main cause of large power system outages. The formal definition is shown here, but basically it's a series of dependent component outages that could eventually cause system blackouts. For now, cascading failures are typically analyzed by quasi statistical models, the QSS model based on AC or DC power flow. The DC power flow based QSS model shows advantages of high computational efficiency, and it can capture cascading mechanisms such as line overload and redispatch capabilities, and more importantly, it can reflect important statistical properties of cascading failures, such as the power law distribution of demand losses, which are widely observed in historical events. Well, however, the DC power flow model neglects the voltage deviations, reactive power flows, and also the transient dynamics. It assumes that no frequency violations or any kind of sudden line overload would occur during this redispatch process, so the system would remain stable before the next failure occurs. But this is usually not the case in real power operation. System transient behaviors actually have a great impact on the following cascading pattern. Also, with the penetration of renewable generation, overall system inertia decreases, frequency issue become more severe. All of this makes the assumptions in the QSS model no longer valid. Well, and in fact, various system dynamics show distinct timescales of operation. So only with a proper representation of time can this model reflect the interactions between the relevant mechanisms more clearly and provide reliable conclusions. Well, apart from this, system evolution also prompts development of new techniques, such as the deployment of information and communication techniques. So how to model these emerging techniques in the QSS model and how to manipulate their simulation assumptions under different operating conditions, these are still open questions. Therefore, there's a need to resync the assumptions in the QSS model to see if they are indicative for future power system behavior. And also there's a need to develop a time-based dynamic model for cascading failure analysis. Here comes the aim of this paper, is to provide an overview of the existing work of dynamic modeling of cascading failures and identifies the main challenges arising from dynamic simulation and also the promising solutions to help overcome these limitations. After this, initial guidance on the selection of internal parameters is provided to enhance simulation efficiency. System responses to disturbances involve a wide range of dynamic phenomena, and they have distinct timescales of operation. The timescales of typical dynamics involved in cascading failures are shown in this figure here. So various dynamic phenomena are shown in the boxes with their distinct operation timescales. So when we have a power imbalance, generation will be redispatched in order to reach the new operating point. And in the meantime, this cascading event can be triggered by protection relays due to the violations of line ratings, frequency, or voltage-related limits. Therefore, the sequence of the cascading events is closely related to the distinct timescale of dynamic phenomenon. And it's important to determine the modeling requirement of system dynamics based on the timescale of interest. There are a few challenges about dynamic simulations. So firstly is the computational burden. The detailed dynamic simulation of cascading process can contain thousands of state variables to represent system behavior, relay actions. So in order to increase the simulation speed, techniques were developed for two main purposes. One was to improve the solving speed of differential algebra equations, which can enhance the efficiency of individual simulation. And then there were also different screening techniques, which are developed to sample the set of initial contingencies, which are going to trigger a cascade. And then we can perform detailed cascade simulation only on this set of contingencies. Another main difficulty is the data, which are required to describe the dynamic features of system components. This data is the basis for the reproduction of an actual power system blackout and for model validation, but they are often publicly unavailable. Therefore, instead of comparing with the sequence of cascading events, another method for validation is to compare the statistical properties of the simulated results. For example, the power law distribution or the heavy tail distribution of the power outages, which has been widely observed in the past blackouts. Our dynamic model is developed in Dixon Power Factory via Python API. Well, details about our model can be found on GitHub via this link. In this model, the synchro generators are modeled as classical second-order model with primary and secondary control. This dynamic simulator focuses on the frequency dependence of system components, which include the frequency responses provided by the synchro generator determined as well as different protection relays. Various types of protection relays are modeled to check for abnormal operating conditions. In our model, all the generators and demand have the measurement devices to keep tracking the frequency along with the simulation and provide under-frequency load shedding and over-frequency generator tripping, and all the transmission lines are equipped with thermal relays. This dynamic model can implement automatic model setup of power system components, controller, and protection relays, and therefore it shows good scalability to be easily applied to large power system models. For other types of dynamic phenomena, such as voltage stability issues, this can be added if needed, without affecting the general method described here. Well, in order to illustrate our dynamic simulators, case studies were performed based on the 200 and 2000 bus networks. A set of almost two contingencies was simulated on both networks. Three cascading risk metrics are chosen in order to quantify the effect of demand losses. Well, firstly, the expected demand of serve, the EDNS, provides an average demand that can't be met due to cascading failures. And then the bind receiver gives system characteristics under more extreme conditions. The figure on the right-hand side here is an example of the probability distribution of demand losses, which can give the relationship between these metrics. Well, let's look at the results. It's often computationally feasible to perform a complete almost-to contingency analysis in large-scale power systems. So we simulated 2000 almost-to contingencies, which are randomly ordered and plotted in different curves here. Well, it can be seen that in the 200 bus system, the estimated EDNS converges to a constant value when the number of failure scenarios exceeds 1000. On the right-hand side, in the 2000 bus system, the estimation of cascading risk is far from converged. And we can see that the estimated EDNS continues to increase, and there is some range in the output here. Therefore, additional failure scenarios are required in order to produce valid risk estimation for this system. The step size is another important factor in dynamic simulation. Basically, a larger step size can improve the calculation speed, but may delay or miss some important cascading event that might occur during this time interval. Therefore, it can change the propagation of the subsequent cascades. Here we simulated 1000 almost-to contingencies based on the 200 bus network, with the step size increasing from 0.01 second to 0.3 second, and the impact of increased step size on the various cascading metrics is shown in this table. The value of EDNS remains nearly constant for step sizes ranging from 0.01 to 0.1 seconds, and beyond this point it starts to decrease. This is because that the increased step size can mask some of the cascading events which occur during this time interval and lead to underestimated risk. And we can see that values of VAR saver and the number of line outages are not quite sensitive to the increment of step size. They remain at a relatively constant level. The errors caused by the increased step size can affect the average demand loss, but has less impact on the extreme conditions where the VAR saver are concerned about, and also has less impact on propagation of cascading outages. A comparison study was performed between our dynamic model and the typical QSS-DC power flow model in order to identify the similarities and differences. The complementary cumulative distribution functions, the CCDF plots of demand losses and the number of line outages are shown here. Well, basically, the CCDF plots indicate the probability that we would have a value higher than a certain level. Let's firstly look at distribution of demand losses. The QSS model, the black line, tends to underestimate the small-scale demand losses. This is because it can't capture the transient system dynamics following the disturbances. This often causes local frequency deviations and inter-area oscillation issues, which can result in a larger number of load shedding. For the distribution of line outages, we can see that the QSS model tends to produce longer cascades than the dynamic simulator in terms of the number of line outages. This is because the QSS model will disconnect all the overloaded lines together, while in the dynamic model and actual system operation, the lines with higher loading will be disconnected quicker. In other words, the overload tripping scheme in the QSS model can sometimes lead to unnecessary disconnections of lines. Well, due to the limited time, there are more results to be found in the paper where you can see, for example, more cascading metrics to be compared. So please have a look at the paper to see more details about this. Well, a quick summary. This paper discussed the state of the art and the future trend with respect to dynamic modeling of cascading failures. The importance of dynamic modeling has been emphasized, and the benefit and challenges posed by dynamic simulation has been discussed. Applications of dynamic simulators are performed based on the 200 and 2000 bus systems. It showed that there's a trade-off between the simulation accuracy and efficiency, which can be implemented by adjusting the parameters. Well, that's all from me. Thank you very much for listening. If you have any questions, please feel free to ask.
Okay, so Yitian is not present, so the co-author and co-chair, Robin Priest, will answer any questions. So I see we already have one question, so please go ahead, introduce yourself.
Hi, Robin. Very nice presentation. This is Daniel Gershon from University of Washington. Please give congratulations to your student for this. I was wondering if one of the issues of the lack of convergence of your simulations is the fact that you occasionally get a complete blackout rather than a small scale outage, and that completely throws off your convergence. That's a phenomenon when we observed a few years back when we looked at those type of simulations.
Yeah, so we certainly see that as the network gets larger, you obviously need to sample a much greater number of contingencies to be able to converge towards meaningful and reliable statistics. For the convergence plot that was there around the expectation, and you'll have to go further to get better reliable results on the tails in particular. And so I think one of the really key things is probably looking into some of those kind of contingency screening methods that Yitian mentioned, but that was more reviewing the literature. It's not something that we've aggressively pursued ourselves. But again, I'm not sure how you would then get guarantees that you're ever going to find the conditions that lead to those extreme cases. I'm not sure. Have I answered? Have I?
Oh, it's a tough problem.
Yeah.
So I'm not expecting you to have a full answer.
No, it's certainly a tough problem. Yeah, we find that, as Yitian mentioned, with the dynamic models, we tend to see fewer big blackouts. Essentially, by including more of the under-frequency load shedding within the model, you're able to stabilize to some point, which isn't complete blackout. So you see a greater number of big blackouts when you use the static representation than with the dynamics. I'm not sure though. Yeah, I'm not sure how you would kind of confirm and guarantee that result. I mean, at the moment, we're essentially doing it by repeated numerical simulation, and I'm not sure what an alternative method would be. So, but yeah, it's a fun topic.
Yeah, Mr. Chertkov, University of Arizona, talking about tough questions. Human in a loop, operator responding, how can we possibly model? And is it good thing or bad thing to have a human, through blackout or maybe disconnect completely? How would you model it?
How do you model
modeling
human operations during? No idea.
Any ideas on how to do it? Any thoughts?
I mean, I guess you could introduce some things that are kind of maybe like probabilistic representations of actions they might take, but how you would build up a reasonable model of how a human operates under those kind of situations, I'm not sure. Short of analyzing past blackouts and trying to determine actions that were taken and erroneous actions that were taken and turn that into some kind of model. But it's not something that we've looked at doing. We're looking at just modeling the stuff that at least we know is kind of hard-coded in there, as opposed to the points at which a human makes a decision. But yeah, it probably should be included because I'm sure it does affect things.
We use the MPC process.
Okay, this is nice
Yeah.
to continue during the panel session, so thanks again, Robin.
Thank you. Sure. So next up, we've got Rodrigo from the University of Sao Paulo, and I think, yeah, this is yours. Oh, and we'll get you kitted up with a microphone, and then over to you to introduce all of your co-authors.
Thank you. All right.
practice helped yesterday. Is it? Are you here? Okay. So thank you, Robin and Kostas, for the introduction. I'm going to present the part of the work or something that we did that is related to the work of my former master's student, Nathalie Gonçalves. And I would like to acknowledge the contributions of my co-authors, André Kernbekele, Tatiana Fernandes, Ada Pavani, and Elizabeth Ratman. So the idea is to design wide area damping controllers considering uncertainty in wind power generation. This is an outline of the presentation, and as usual, this is pretty straightforward, so I will skip this and go right into the explanation. We all know that wind power has a stochastic nature, and so it will affect the operating point, and we cannot predict in a deterministic way how the input of wind power plants will affect the operating point of a power system. For the purpose of controller design, we can use numerical methods to sample and to get operating conditions that cover the whole range we can sample the whole range of possible operating conditions. But the problem is that they are usually very time consuming and require high computational efforts. Now, here's a question. Do we want to represent the entire possible operating region, or do we want to put an emphasis on the most important conditions for us, which are the worst case scenarios? And that leads to the issue of sampling to represent the entire region of operation versus sampling by importance. So in this case, sampling by importance seems to be much more intuitive, because you're more interested in the problematic scenarios. So what we did here was exactly to propose an approach based on the cross-entropy method to compute combinations of wind power deviations that deteriorate the small signal stability margin of the system. So when we use that, we're able to compute a set of conditions of interest which are worst or which are the problematic scenarios, which should be included in the design, together with other representative operating points of scenarios in which the system is not under a threat of instability. So how did we do that? The first thing to note is that for short-term horizons, wind power can be well described by the beta distribution. And in this way, if you assume that a certain prediction represented by a normalized predict power, if you assume that, the occurrence of some particular power output value of the wind power plant is given by this beta function, this probability distribution. So we can plug this in to a cross-entropy method, and then this is the cross-entropy approach that we are proposing. Now, I'm not going into details again on the whole algorithm, but the main feature that I will highlight here is that this method is able to generate what we call an elite set. The elite set is a set that is composed by the most important samples of the distribution, of the probability distribution. And for us, what is most important is what poses the biggest risk to the system. So we generate random scenarios through sampling of the of that previous function that I have shown you, and the algorithm iterates, preserving the ones that are problematic scenarios, and then converging to making combinations of them by updating parameters of the distribution at each iteration to be able to generate worst case scenarios. And then I have a set of n, not worst case, but problematic scenarios. And then I have a set of n samples with a stopping criteria. Hopefully I get the worst case scenario within this set. Then I can use it for damping controller design purposes. Here is the architecture of the wide area damping controller that we are proposing. So we have the power system here. We have measurements taken from the PMUs. They are sent to the wide area damping controller. There are delays in the communication. The wide area damping controller, which is at the PDC, then processes the signal, sends the output signals with the corresponding delays as well to the local controllers, and then the local controllers act on the synchronous machine to damp the oscillation. Now, one thing that I need to explain about this figure, this picture here, this figure actually, is that it may cause some confusion. What we are doing, we are not plugging the output of the central controller into the PSS itself. It might convey the wrong idea. What we're considering here is that the summing junction of the AVR is part of the PSS. So the contribution of the WADC is a supplementary signal to the supplementary controller, which is the PSS. So they're superimposed, just to make things clear. Well, then here is the test system that we use to test the the results that we could get from this approach. And well, this is a modified version of a benchmark system for small signal stability studies, which I had the pleasure to be involved. I had the pleasure, the honor to be involved in the task force that set up these benchmarks. And what we did here is that we modified the benchmark, and the bus bars you see here in red are the ones in which we inserted wind generation. So the operating point of the benchmark system changed, and as a result of it, if we calculate the least damped modes for the system, what we see is that we have two inter-area modes which violate the 5% damping criterion So the system is not secure in this base scenario without the damping controller. But this is the base scenario, and we've already seen that because the wind power that with nominal values of the injected power already perturbed the power flow of the system, it changed its equilibrium, then the damping, the security, was criterion from the small signal stability viewpoint was not met. So we have to do something to enhance it to 5%. But this is for the base case scenario. What we want is to see if with fluctuations, stochastic fluctuations in the wind powers that we modeled, if we can get even worse scenarios than this one. So we used our cross entropy method, and one thing we have seen is that this method is really effective because it converges very rapidly. For example, in terms of the least damped mode that I have shown you in the previous slide, it started here at around 2.4%, and in 3 iterations, it converged to a set of elite samples. In this set, there were we chose 20 scenarios, and among these scenarios, there was one in which we found 1.9% of damping. So this is certainly the one that must be included in the design stage to make sure that the controller is able to properly damp the electromechanical oscillations in the presence of wind power. Now, when we designed the WADC with this assumption, well, we could achieve the 5% damping. Now, to illustrate that, I have a plot that shows the behavior of the system with the without the WADC, without the wide area damping controller, and with the wide area damping controller. And at this point, you might wonder, well, why would you make such a huge investment to come up with this infrastructure of communication, installing PMUs, and just to get this very little, very small improvement in damping? Well, the first thing to keep in mind here is that we're not proposing that this is a structure that needs to be dedicated. We suggest that this could be an existing infrastructure that could be used for this purpose as well. So there's not much investment, additional investment needed. And the other thing is, yes, this is a small contribution, but, and we could aim for a much higher value of damping. Why didn't we do that? Because small signal stability is tricky. If you aim for too much damping, and you only analyze from the linearized viewpoint, you might be saturating the controllers, the AVR, for example, and then the damping values that you see are not will not be reflected in practice. So yes, it is a small additional help that comes with not a large investment because the infrastructure is already there, and we can improve the system damping in this way and still avoiding saturation of the controllers. These last observations are actually my conclusions, so I'm going to skip right to the next, the final slide, and thank you all for listening.
Thank you very much, Rodrigo. We've got time for a question. I think Claudio's already made his way, and then maybe we'll have time to squeeze you.
We can fight for it. Interesting presentation, Rodrigo. Claudio Canizares, University of Guadalupe. I was curious, a few years back, I guess by now it's many years back, we were looking at applying interval arithmetic, affine arithmetic, to trying to determine what the impact of these variations were on the system. Now, what we noticed is that when the system is stable, that was meaningful. But when you get into margins of instability, those results in the margins told you that one side is stable, the other side is unstable, not very meaningful. And I wonder whether in these studies where you were looking at these variations of wind and solar, you look at that issue and whether that was useful in any way in designing your controller?
Thank you, Claudio, for the question, because this gives me an opportunity to give yet another explanation. I assume it was Alfredo that was during this investigation.
It was involved, yes.
Yeah, you are correct. If the system is unstable, the results are not meaningful. But one thing we kept in mind is that we cannot rely on the centralized controller to be the main contributor to damping, because it is subject to cyber attacks, to structure failures, to several other things. So you might have to disconnect it. And when you disconnect it, you have to rely on the PSSs to render the system stable. So we only considered the situations in which the system, when the controller was taken out, was still stable because of the actions of the PSS. I don't know if that answers your question. Okay.
We have time for another? Yeah, just a short one. Okay.
Okay, so João Peças Lopes, University of Porto. Thank you very much for your presentation, quite interesting. I think that the wind generators are the ones that are going to excite those oscillation modes, right? Because my question is the fact that being the system with wind generation that brings those oscillation modes, or the oscillation modes are excited because of that wind generation? You see the point?
Yeah.
Because I think that the oscillation modes are already there. You just need to afterwards to find out a solution, and the one that you presented seems to be very, very interesting and effective. But it is not because of the wind generation, right?
Well, to a certain extent, yes, you are absolutely correct. The oscillations are there. They are electromechanical, and they occur between groups of generators that are synchronously connected. The wind generators are kind of isolated from this because they have a back-to-back converter but yes, they do impact the oscillations because they change the operating point. And that is the main issue. And they impact they change the equilibrium point in a way that you cannot predict with deterministic methods. So that's why we actually have to sample to find out the problematic scenarios and include them in the design. to make sure that these, the effect of the wind power over the electromechanical oscillations is accounted for.
And at the end, you have a robust design.
Yes, yes. The whole purpose of this is robustness.
Brilliant. Thank you very much. I think we'll save anything else for the discussion at the end. So thank you again, Rodrigo. And if we could not travel too far. So hopefully we'll get you hooked up with the stuff, and you've got this clicker, which all seems to be working. So over to you.
All right, good afternoon, everyone. Thanks for being here still. I know it's a little bit late, but thanks for being here. I'm Mohammad Mansuri. I just graduated from the University of Calgary. I defended my PhD 2 months ago. My supervisor are Andy Knight and David Wick. And now I work in BBA, but now I represent the University of Calgary. My presentation, my paper is about the force oscillation. I developed an N-forced algorithm based to identify the source of the force oscillation. In this presentation, I'm gonna first start with the introduction. I'm gonna talk about the importance of the identifying and mitigating of the force oscillation. After that, I talk a little bit about the PMUs. Because I use the N-forced in my algorithm, I talk about the N-forced. I'm gonna talk about my algorithm, and we review some simulation, and I'm gonna finish with the conclusion. The force oscillation is a damped sinusoid signal that usually have external sources. In the mathematical model, we can model that with the summation of the damped sinusoid signal. As you can see here, I still try to learn to work. As you can see here, there are a damping, frequency, and magnitude, and all of them are unknown parameter. And it's unpredictable usually. We cannot predict that it can be the sustained or poorly damped oscillation. Force oscillation, as I said, usually have external sources. For example, a malfunction in the mechanical part can cause the force oscillation. One of the challenges for force oscillation is that it happens usually at the same frequency with the electromechanical oscillation. And a lot of algorithms that is in this area, they cannot distinguish between the force oscillation and electromechanical oscillation. When it comes to the force oscillation, we usually try to identify the source and isolate that part from the system. We cannot, for example, design a controller to mitigate that. We usually need to look at the source and isolate that part from the system. But why the force oscillation is important for us? Why we care about that? This usually causes the increase in the maintenance cost. It can decrease the or limit the power capability, and in the worst scenario, it can even cause the instability in the system. Okay, if I want to categorize all the methods in this area, we can categorize them to the measurement-based method and model-based method. As we can guess from the name, the model-based method needs the model of the system. We have a dynamic of the system in advance. We study that, and sometimes we can predict them. But it's not an effective way. The utility right now are more focused on the measurement-based method. Measurement-based method work with the real-time measurement from the system, from the PMU, and they work based on this measurement, and they don't need to know the dynamic of the system in advance. And right now, because of the PMUs, we can easily implement the measurement-based methods. As an example, in 2009, we just have around 200 PMUs here in the North America, but this number increased to around 2,500 in 2017, more than 12 times. And now we have a lot of data, we have a lot of measurement from the system that can help us to work on the measurement-based method. As another example, with the PMUs, we can have around 30 to 60 samples per second, but SCADA data is just give us one sample every 2 or 4 seconds. Here you can see that the difference between the measurement from the PMU and SCADA. Okay, if I want to summarize so far, what I talk about that, I talk about the importance of the force oscillation, why we are care about them. And in the second part, I talk about the PMUs because it's the tools that we can use with the force oscillation. Therefore, I came up at the result that I'm going to develop an algorithm to look at the source of the force oscillation. My method is based on the bolide identification. In the classic identification, we have the input data and we have the output data. We consider the system as a black box and extract the dynamic of the system based on the input and output data. But in the bolide identification, we just have the output data from the system. We extract the dynamic of the system only based on the output data. And here in PMU, we have output data. Because of the PMU, we have the output data. And the method that I use it is a bolide identification. There are a different bolide identification in the literature in the control theory. The method that I use is a subspace, a state space system identification that called the N4C. N4C have 4 standard models. The model that I chose is the forward innovation model. The reason that I chose this model in the modeling, in the mathematics, it's easier to extract the parameter of this method. And in my application, because I want to also extract the input, this model is best fit to my work. I try to conceptually explain the N4C, and after that my algorithm. Each of these steps is full of the mathematics. I don't want to go through the mathematics. I try to explain that step by step in the conceptual way. What we're doing in N4C, the first we receive the data. We divide the data in 2 parts. We call them usually in our notation the past data and future data. We form the Hankel matrix based on the data that we have. We calculate the projection. After that, we're going to do the SVD, singular value decomposition. When we do the SVD, we're going to have a different eigenvalues. Based on the order of the system, we have a couple of eigenvalues as the big number. After that, the rest of the eigenvalues in our SVD going to be almost 0. And in the rest of the calculation, we can just ignore the eigenvalues that is almost equal to 0, and it increases the calculation load for us. In the second step, we chose our model. As I said, in this study, I chose the forward innovation model. After that, we extract determine the state vector, extend observability matrix, and in the last step, when we arrive to the last step, we're going to have this model from the system, and we're going to have all parameters from this system. Now, what is the algorithm? What I'm doing here, in my algorithm, in the first step, I'm going to receive the data from the PMUs. I put the data in the terminology of the N4C. In the second step, I choose my model. As I said, it's a forward innovation model. I extract the parameters of the model, by using the enforced. In the third step, I extract the input of the system. What I'm doing, for example, I have a 4-bus system. In each buses, I have a measurement. In these buses, I have a response of the system to the fourth oscillation, but I don't know which one is the source, and I don't know which one is the fourth oscillation. I have response of the system to the fourth oscillation. After that, by measuring this output, I extract the dynamic of the system. I extract one input in each basis. Now I have 4 inputted that each one might be the fourth of oscillation. Actually, one of them is the source of the fourth oscillation. Others are the response system to that. How can I identify which one is the source? The first thing that comes to my mind, the signal that is the source should have more similarity to other signals. For example, if I have a 3-bus system and the bus 1 is the source, if I see the similarity between bus 1, bus 2, bus 1, bus 3, bus 2, bus 3, the one that is the source should have more similarity with others. In the statistical mathematics, this means the correlation. To check that, I calculate the correlation between the extracted inputs, and after that, the one that have a higher correlation with other inputs gonna be the source of the fourth oscillation. I have one simulation here. I simulate the 4-machine 2-area system. I have 4 bus here, 4 measurement and 4 bus actually. Here I inject a fourth oscillation in generator 1. I apply my method to this system. I get the measurement from bus 1, bus 2, bus 3, bus 4. I extract the dynamic of the system from the measurement. I didn't have any dynamic info in advance. I extract the dynamic of system from the measurement. After that, in each bus 1, bus 2, bus 3, and bus 4, I extract the input. I assume that I have one input here, one input here, one input here, and one input here. Now I have some extracted input. As I said, the one that is the source should have more similarity with others. To check that, I calculate the correlation between them. Here in the first plot, I calculate the correlation between extracted input in bus 1 with bus 2, bus 1 with bus 3, and 4. The second graph, the second plot, I did the same for a bus 2. If I check all these graphs together, I can see that the correlation between the bus 1 and correlation between the extracted input in bus 1 and other bus is higher than others. And therefore, I can come to the result that this is the source of the fourth oscillation, as I know is true. And thank you. I'm almost done. One of the advantages of my algorithm is that this algorithm can distinguish between the fourth oscillation and electromechanical oscillation. As I said, this is a challenge in this area. To check that, again, I use the 2-area 4-machine system. I trigger the electromechanical oscillation by switching out and switching in this load. Now I could trigger the electromechanical oscillation in the system, and I apply my method, and again, I calculate the correlation between the different extracted input. Because the electromechanical oscillation is part of the dynamic of the system, this is a natural mode of the system, it doesn't have any input. I expect that I should not have any meaningful relationship between the correlation, and this is what happened. there is no meaningful relationship between them. If I have something like this, I would say that it's not I don't have any force oscillation, and it is true based on the knowledge that we have, and we know that. Okay, in this presentation, first I talk about the importance of the force oscillation. I talk about the challenge in this area. After that, I talk a little bit on the background in mathematics and identification. And finally, I explain my algorithm and show some simulation. Thank you so much.
Thank you. Thank you very much. We've got time for a question. I'm going to go to Panos just because you've already had one this session. So.
Hello, Panos Papadopoulos from the University of Strathclyde. Thanks for the presentation. Just a quick one, actually, about the choice of the subspace method. So, is there any particular reasoning? Have you tried other methods, and did you see this performed better compared to the others?
Actually, I didn't check other methods, but one of the reasons that I use this method, because in the subspace identification, we use the SVD, and this kind of makes the system robust against the noise, and we work with the measurement. That was one of the reasons that I started with the subspace identification, but I didn't check other methods.
So did you try adding noise also to the simulated signal? Or?
I don't have a result here, but yes, I interpret the noise in the signal, and the result was.
Good, thank you.
Okay. That was nice and quick, so if yours is also quick, you're welcome to go, Claudia.
Claudio Canizares, University of Waterloo. Interesting work. I guess about 15 years ago, we were working on subspace identification methods for similar applications you have here. Now, one of the reasons for doing this was we were trying to detect noise, the eigenvalues from or identify the system from the noise, from low perturbations rather than big perturbations. So my question is whether you looked at that problem using this type of techniques, which seem to be appropriate for that, and whether you compare this with more common methods that work well when you have big perturbations, which are very much using this type of application in the Western interconnection of the US, PRONI and those type of methods.
The PRONI's method, for example, matrix Wenzel, Maroney's method, all of them also come from, I think it's the 80. For example, PRONI method is not robust against noise, as far as I know.
Correct, yes.
In the matrix Wenzel, when you want to show the parameter, you have a lot of parameters. For example, the window that you're choosing, the number of the mode that you're choosing, is one of the challenges that we have, because I implement the matrix Wenzel as when different modes have a different accuracy.
Correct, yeah, I'm aware of that. But these methods are more for noisy type of stuff, but I didn't see that in this case. Thanks.
Which one? Sorry, can you?
Did you consider noise in this case?
No, in this case, no.
That's what I'm asking.
I have simulation with the noise, but here, no, in the simulation that I showed.
Thanks.
Okay, thank you very much. Another round of applause. And next up, we have... Next up is Johanna from ETH, who is going to be talking about active distribution grids and parameter restoration, I think. Over to you. You can either stay there or...
Yeah, no, it's fine like this. Thank you. Thanks for the introduction. I was already very excited to be here, but the discussion that actually I think Ian triggered on Tuesday about needing to integrate loads and have more robust models got me even more excited to be presenting this work here today, because what we're aiming to do with this work is really using quantized forecasts to not only say what is like the median response that we can expect from a distribution grid, but what are kind of the best and worst case responses. So this work is part of my PhD that is supervised by Gabriela Hug as the main supervisor, and then Petros as well. And Thierry Tsufri is like, in our group, the machine learning person who has helped me with the quantile forecast part of this work. just a bit of a background. I mean, we're all aware, because we've heard also this on Tuesday already, that we have more and more distributed resources that actually also supply ancillary services on transmission grid level, which means if we want to do suitable stability studies, we somehow need to incorporate them in our studies, so we somehow need to incorporate them in these large systems, which can be a very computationally expensive task. And there are two current approaches so that we do equivalencing, and one of them we've also seen on Tuesday, the one on the left-hand side. There was a gray box model derived that keeps the physics of the system, but most of these that are out there in the literature actually are usually for voltage stability studies, so they use only short circuits for their training, or they ignore the uncertainty, or if they do include uncertainty in the sampling, they don't preserve it in the equivalence, so they just still provide a mean response. Then there are black box models. The second line also holds usually for the black box models. And the third line there is also very significant, so most of the ones that have been tuned have actually been tuned on data that was coming from actual grids, which then does not have the severe cases in the data set, or they were not tuned on a rich data set, which is very important for machine learning. So the approach that we are suggesting in this work is a simulation-based approach where we start with Monte Carlo simulations of our distribution system. Then we tune a quantile forecast, which means that we don't just predict the most probable response of the distribution system, but we can also say that we have, for example, what I have here, we want a 90% confidence that our response is going to be within a certain band. And then what we can have as a result is not just the most probable response, but we can have a band of responses that we can expect. So this is the method and the contribution, and will also be the outline of my talk. I'm first going to talk a bit about the generation of the data set. It's actually been a work that I presented at PSCC, so I'm not going to focus that much on it. I'll show you quickly how we have done the tuning, and then I want to speak more about the results of this case study and some further assessment that we did on the robustness and suitability of this method. So the grid that we've been basing this on was really a 0.4 kV grid from SICRA that you can see here on the top left. We have very recent load models and PV models in this, so both are capable of supporting frequency and voltage. Furthermore, we have also modeled all of the standard protection in them. We have actually applied the Australian grid code there because they have one grid code that's for this very low voltage level, and they also incorporate batteries, which we have then used for load parameterization. There are a lot of sources of uncertainty that exist. We have included the ones that are here in blue, so we kind of assume that we know the operation point. However, all of our model parameters are unknown within a given interval. We also don't know the load distribution, so the distribution among our thermal loads, induction machines, and also exponential load models is unknown. And then we also test for different disturbance sizes, so we have a larger set in that. So overall, we have selected first a strong transmission grid equivalent that is also represented by synchronous machine. We have drawn 100 parameterizations and then run for each of them 10 load steps. That gives us 1,000 time series and a very rich data set for our tuning. That is what you can see here. So you can see here the time domain response for voltage, frequency, and the current across the transformer. And then on the right-hand side, you can see the maximum frequency deviation, rock-off, and currents for each of the different disturbances and their mean and variance. So you can see that we actually have quite some variance in our data, especially for the currents. So then the next step was to tune the machine learning methods. The implemented algorithms you can see here on the left-hand side, we have not included the support vector machine in the results because they were generally poor, and there's also no quantile version of it. We have decided to use also former inputs. So as you can see, our inputs are not just voltage and frequency, but we also use former currents. So our configurations for training and testing are different because in the training stage we have, of course, the currents of the former time steps, but during testing or in real operation we don't have that. Yeah, we have done extensive feature selection, hyperparameter tuning. All of that is in the paper. I don't want to bore you with that here. And then for the comparison that I'm going to show you now, we trained with 800 series and tested on 200 series. So let's look at the results. You can see here an overfrequency event and an underfrequency event and how all of the algorithms perform. I think it is quite clear that in the general picture looks quite good, while the transients we actually have quite some mismatch. This especially holds for the reactive current that you can see on the bottom. And then for the active current, we also have some mismatch, but we also have some methods that actually fit quite well. This is just one example, so we ran proper analysis. So here on the left-hand side, you can see traditional metrics that are being used in machine learning. So you can see there are two-square root mean square error and mean average percentage error. The second, this din here means that this is only the error evaluated during the transient period, which should also be quite exact. And then on the right-hand side, which is more important for actually time series prediction, we've looked at what is the forecasting power of our model, because a model that is a persistence model could actually also perform well on the traditional scores. But what we want in our model is that it actually can predict the change from one time step to the next well. And this is what we can assess with this metric. And ideally, everything would be on a line. And the score would be 1. And we can see that the performance for linear regression, for example, is quite poor, which would, and then for others it's better. In general, the GBT, so gradient boosting trees, have provided the best point forecast, considering both metrics. Linear regression is very good on the traditional scores, but not on the time difference metrics. And then the neural networks are better on the time difference metrics. And because of that, we have taken the neural networks and the GBT to the quantile stage. So the quantile forecast that I'm going to show to you now, I just want to explain how to read these plots a bit. So you have always the actual response in black. Then in red and in yellow, we have the 50% quantile and the point forecast. I put both because the loss function deviates slightly. And then in blue, from light to darker blue, we can see the intervals with different confidence. And what we can see here nicely is that the smaller the confidence, the tighter our bound gets. And what we can also see nicely for this neural network here is that we have kind of the symmetric band around our actual response, which is very desirable and what we would like. What we can also see here is something that we really don't want to have. This means that our forecast here in this period is not reliable. Oops, here, because our actual response is not within the band. So here you have an overview of all the different forecasting techniques for one specific step. We have also done quantitative analysis on this. This is in the paper with some quite large tables. So I just wanted to provide you with the key findings of that. So all of them show similar performance for reactive current, which during the transient is quite poor. The GBT performs poor for high confidence because we have very wide bands here. This is somewhat undesirable. And we can see that the neural networks in general have these very nice bands around our actual response. However, we need to trade off the sharpness and reliability because we usually would like thin bands that are sharp but reliable, and there's a trade-off between the different methods here. Now this, what we've done so far, was just an assessment on, well, how well does our machine learning work? So as I said, we wanted to do 2 additional assessments, and the first was actually that we wanted to try to generalize this approach a bit and see what happens when we test this data on a different transmission system. So what we have done is that we have reduced the grid strength and inertia of our transmission equivalent, and then we ran again the Monte Carlo simulations, and we have tested our trained equivalents on the new data set for the weak system. And what we find there, so here again you can see 2 of the quantile forecasts. What we can see is the performance on IQ gets even worse. But there's also good news because the bands in general were actually becoming wider, which means that our algorithm is correctly detecting that there was a change in the data set and that there is higher uncertainty, which is also what we would like, so that it's providing us with a more conservative forecast here. So there's a bad and a good result here, or one to work on, let's say that. Then the second additional assessment that we did, because again, we would like to place these then in actual transmission grid studies, was that we wanted to look at how well do our intervals now overlap with our Monte Carlo simulations. So the way we did that, so this was just one qualitative assessment. We have taken a random series, one random series, and then plotted that one, did the forecast and plotted that against all the trajectories, and that's what you can see here. So as somewhat expected from the previous results, all of our reactive current transients are somewhat out of the bands, so there really needs to be some work done on this. But the good news is that for the active current here, for example, we can't even see a single of the Monte Carlo trajectories, which means that they are within the bands. I have actually also checked that numerically, so if we have a neural network with a high confidence, we are performing quite well on the active current. So these are the findings here. However, the disclaimer is that this is, of course, very preliminary because it's only based on one time series, and we're going to need to look at quantitative assessment here as well. So that brings me to my takeaway messages, questions, and outlook. So what we've done in this work is that we have proposed these quanti-forecasts to be used to represent the uncertainty that we have in distribution grids in large-scale transmission grid studies. However, there is then the question, if we have a lot of these quanti-dynamic equivalents next to each other, how do we operate them? Because we're going to have 3 responses from each of them, and which is like, is the worst case then really a realistic case, and so on. So these are questions that we need to look into in the future. We have successfully tuned some of the machine learning methods. Surprisingly, the linear regression also performed very well. We are also planning to integrate that also as a quanti-forecast. We have seen that the performance on reactive current was quite poor, which might be the case because we've only used load steps, so we're also going to use voltage dips to try to get better on the reactive current. Thirdly, we have seen that the tuned equivalents are robust against changing transmission grid conditions, which is very good news. And then last but not least, we have seen in this one preliminary result that the current trajectories overlap well with the Monte Carlo simulations, but again, we need a quantitative comparison, and then we also need to reintegrate that back to our simulation platform, which is what I'm working on right now, to get our neural networks back into our simulation platform. With that, I would like to thank you very much for your interest and attention, and I'm looking forward to questions.
We'll start with Patrick, because he made it there first.
Yes. Patrick Panciatici from RT France. Thank you for the very interesting presentation. Just a clarification, in your simulation there is no tripping of the power electronics.
No tripping?
Yes.
There is.
There is?
Yes. So I've in the models there is over frequency, over voltage protection, all of that, rock-off protection.
But in your simulation?
You can, so I mean, I only showed a few of the time series. You can actually see that in some of the simulations. But I mean, the time series I have shown was the current across the transformer. And in the cases where it trips, I'm not sure I have a case in the presentation. But I'm sure there is one in the paper, okay. But it's there, and then you see the jump of the power,
okay,
in the power.
You.
Yeah.
Thank you.
Okay, thanks. We'll go to Rodrigo quickly, and then maybe Deepa.
I had to be faster than Claudio because I didn't want to ask a question as a panelist. First of all, congratulations for the very interesting presentation. And my co-author, Ada Pavani, presented on Tuesday on a very similar topic. So I'm happy to see that there's a lot of interest in this topic. Now, you've shown under frequency and over frequency events
and you had to tune your model for these events. Where are these events happening, and what are they?
These events would happen.
The event that triggered the dynamics of the dynamic response of the ADN.
Yeah, so they would happen in the transmission system. I have added a load in parallel to the generator. This is how I did it in the simulations, and then I did like step changes for that load. So, like you would do that in the classic way to do that in frequency stability studies. So it would be transmission grid faults.
Okay, so one issue that we have faced with this approach is that the amount of perturbations that occur in the transmission system that propagate to the distribution system up to an extent that there is some significant tripping of distributed resources and all this. The set for training is quite small because you don't have these many perturbations that propagate and generate a response that gives you observability enough for you to be able to tune the parameters. Do you see the possibility of simulating faults within the distribution networks that happen much more often as a way to have a larger training set to be able to estimate the parameters? Is that a feasible alternative?
So I did not experience, because I can, in this work, I can select the disturbance size that I have in my transmission grid, and I selected them in such a way that actually all of my protections get triggered. So I made them so large that in both directions I have triggering of my protections. And then regarding the disturbances within the distribution system, I think that would be possible because, then in the end it's a machine learning algorithm and I'm just trying to match the power that is flowing over the transformer. So that would be some future step to look into, but I think it should be possible.
Okay, thank you.
Thank you very much. I don't think we're going to have time. Could you save it for the discussion? Is that right? Sorry, just to make sure we get our last presentation. So thank you very much again. And we will move to our last presentation, which is Adam from Texas. Do you want to stay here, or do you want the...
I'll stay here. This will be fine.
Perfect.
It's 15 minutes, right?
Yeah. And there's that if you want it, or I guess you're...
I want to greet everyone with howdy from Texas A&M University. I'm here representing our group, and we have a large power system group there, and there's our research lab, and wanted to show some pictures of where we're coming from. It's really good to be here in Banff and to escape the Texas heat for a little while, and so I appreciate this opportunity to come and talk to you a little bit about some things that we're working on. I'm working on building synthetic electric grids. And the motivation mainly for this is that there is a need for high quality, large scale, and realistic public test cases and power system models for research and development in a lot of different applications. Of course, we have real grid models, but for the most part, they're not publicly available. They're restricted for legitimate security reasons, and if you are a researcher and you have access to real data, it's usually under a non-disclosure agreement, and it's difficult to publish and communicate your results. I think that it really benefits science and research in general if we have data sets that are public to the point that peer researchers can cross-validate each other's results. And we have, of course, the IEEE test cases and some other test cases that have been brought up in various presentations during this conference, and you see lots of papers and journals and so forth about them. They're really good for initial studies, but for the most part, they're rather small, and when you compare them to actual power system models that you get from industry, there are big differences, not only in the order of magnitude of size, but in the complexities and in a number of different metrics. So the grander research effort that this paper is part of is building large-scale synthetic electric grids. And here's an example here. If you're a little bit familiar with the Texas power system, you might think that this this model may be the real Texas grid. In fact, the generation distribution and the transmission network and all of that is pretty similar. But if you're very familiar with the Texas grid, you should be able to notice, if you look at it in detail, that in fact the transmission network itself is totally fictitious. It's fake. It's been built with an algorithm. We have a suite of algorithms, in fact, that are used to take statistical information about real power systems and what they're like in terms of graph theory, in terms of engineering design criteria, and in terms of geographic constraints, and replicate those in fake cases, as it were. I like to say that they're fiction, but hopefully very good fiction, and therefore quite useful, we hope, for lots of research applications. And in fact, I was set up very well by the first presentation of this session, which talked about using the 200 and 2,000 bus test systems, which are part of our suite of test cases. This is 7,000 buses. If it's not big enough for you, I've got a 70,000 bus one of the eastern US. So we want to make sure you have plenty of data available to test your algorithms, your great research results, and scale them up to industry-sized cases in a way that then you can totally publish those results and others can see them and check your results. So that's the big picture here. The direction that I'm really wanting to go with these, we have really good static models here, is building dynamic models for synthetic grids. Of course, here I just put a picture of the 9-bus case as an example here of kind of a standard test case that we have. What we want to do is take the ones like I showed on the previous picture of the large 7,000 bus case and create realistic dynamic models. This is order of magnitude probably larger, harder problem. How do we build a realistic synthetic dynamic test case? But I think it's important to help support and spur innovation with large transmission system research. And so the main goal here is to show that a test case is realistic, to build a test case with all of the dynamic parameters and all of the complexities in it in a way that it is similar to the real grid, but totally public and not containing any confidential information. There's been some work that's been done on this already. In fact, at a prior IREP, and the initial approach and the work that's been done so far is based on statistical analysis of real grid dynamic models that we have. So we figure out the different parameters of the devices, let's say the reactances of the machine and the control gains of the governors and exciters, and we have an understanding of statistically what those parameters look like. But the challenging part of this problem is the fact that all of those interact in very complex ways in the way that the dynamics of the system works out. And we have some performance metrics, things like the frequency nadir and the voltage recovery and not having too large of oscillations, but it's an ongoing problem to validate these cases and to show that they really behave in the way that actual power systems do, and to see how we can kind of tune these parameters of the models in order to make them do that. So that's what we're trying to do here. And one step that I was trying to take forward with this paper is to start looking in more detail at the frequency response and inertia aspects of synthetic cases and see if we can mimic the way the real grids behave on synthetic ones. And so that's kind of the direction I'm going here. And the way that large-scale transmission systems work is that you have all this rotating inertia in the synchronous machines, and if you have a large loss of generation or another contingency, that inertia serves as a fast frequency response effect where it almost immediately begins to supply the missing power and arrests the speed of frequency decline until other control systems can come into play. And at a system level, you can just look at the swing equation and kind of get a zero-order approximation of what happens in a system when you have a loss of generation. You have the swing equation, which one of the key things we care about is this idea of the rate of change of frequency, Rokov. And say rate of change of frequency, rate of change is derivative, so derivative of frequency. You look at the swing equation, there's derivative of frequency right there. So if you rearrange that and you kind of have this summation formulation, nothing new here, of course, you can kind of get a zero-order approximation of what the frequency ought to be doing just based on what all of your inertia parameters are, your H parameters, and the MVA base of the different generators. Of course, this is kind of aggregating everything all together. So you look at the 9-bus case, that picture on the right, and you can see that if you lose generator 3, you should have a frequency response characteristic, sort of like the yellow line there, and there's the actual one blue as the other complexities of the system start to deviate from there. How is this analyzed in ERCOT or in a real system? ERCOT, just taking it for an example, ERCOT measures the system-wide inertia with summing up H times S base, just like I showed on that equation on the previous slide. And so they're monitoring their inertia level using this summation metric. And it varies, of course, based on the load, what wind is in there, and dispatch. Of course, there's just summing it up for all the generators is for the real system is conservative because there's additional inertia and load. And so the minimum in 2017 was 130. It's continuing to go down. And in 2021, the lowest it got to was about 116 MVA seconds. They've done some simulations, and they've concluded that 100 MVA seconds is approximately where you might have to reconsider some of the current operating practice. And there's a plot that is from one of their reports just showing the different scenarios that exist and the different inertia levels that are out there. And of course, there are other grids doing different kinds of studies. One thing that is coming into play that I wanted to see if we could make a little progress on when it comes to how do you analyze a model and analyze how frequency response and inertia is all interacting together is to start to look at this idea of locational impacts of inertia, where the inertial resources and by extension other frequency response resources are located. And that reminds me of a couple different presentations that we had earlier in this seminar, or in this symposium, that's the word. So I wanted to look into that a little bit, and I wanted to start at a very big level, start at 7,000 bus case, and just see if we can make anything beyond this summing up of the inertia everywhere. And so the goal here is to keep this framework of a very simplified zero-order relationship between inertia and the Rokoff, like not add a lot of the complexity to it, but go ahead and make the jump to a 7,000 bus case with all of the network effects represented by the Y-bus matrix of the impedances. And so that's what I've done here, and I've started with this current injection model. So you see those equations there on the third line are basically the multi-machine system with classical machine model. And then what I'm doing is I'm deriving this idea of inertia adequacy measure on a locational basis where we can get an approximation for what the second derivative of the voltage angle would be, which would be the first derivative of the voltage frequency, which would then be an approximation of the Rokoff. And so the derivative follows there through the bottom of that slide, where we take an initial condition and then we change the Y-bus matrix and the current injection vector to represent some arbitrary contingency that we have. Therefore, we can model the variations in where the contingency actually occurs. And then you have these equations here where you can calculate this value V double dot, that is the second time derivative of voltage, and then you remember back to the trigonometric derivative equations, and you can get an equation for the second derivative of the voltage angles. And now we've got a vector that's a zero-order theoretical estimation of the initial second derivative of the voltage angles. And we use this as a potential screening mechanism to get an idea of how the impact of the location of the disturbance and the location of the inertia resources can affect the varying frequency response. And so the good thing about this is it's very fast. We can just do it. It just takes 2 matrix calculations each. And so we did 20,000 test cases in a short amount of time. And so we have the 7,000 bus case, very large case. I made 125 base loading cases, so all different levels of wind. Texas is the #1 state for wind, so we did all kind of levels of wind, all kinds of levels of how much synchronous inertia is connected, including realistic and maybe will be more realistic in the future. So all kinds of things, and then lots of different contingencies, including the benchmark contingencies, smaller ones, and even some larger ones as well. I set up to 5,000 megawatts. I think there were some that were getting even larger than that, up to maybe 10,000 megawatt contingencies. So we got 20,000 cases, and I can run them pretty fast. And so we can, again, this is kind of a screening mechanism to kind of get an idea and maybe isolate some individual cases where weird things are interacting in a large system. And so here's a picture of the results. It just runs in a few hours and much faster even than a steady state contingency analysis. And then you get these results where this blue line is showing, okay, we have a contingency generation loss. This, by the way, is just one loading case. And this is the initial metric that I showed for system-wide level, what the Rokoff should have been, and then the calculated values for what it would have been at each individual bus, summarized by the maximum, minimum, and average. And so there shows a lot of data on that one chart. But this data is available very quickly, and therefore we can kind of, from this, identify particular cases, particular loading cases, particular contingencies that might have some interesting phenomena going on. And next, what we can do is we can kind of pick one out and dive into the details. So here's this 7,000 bus Texas case again. I picked one 1,300 megawatt. So it's a case where it has low inertia and you or inertia configured in a somewhat unusual way, and you've lost 1,300 megawatts of generation at the location indicated there by the blue dot, and it just showed some interesting results in the screening, and so I ran a full dynamic simulation with it, and it gave this very interesting result where you saw the frequency, there looks like a fairly normal frequency response there, where you have some separation in the different areas. It turns out that some of our under-frequency load shedding models triggered in this simulation. When you look at this, it looks like it might not be able to read those numbers, but the 8 buses that are plotted there don't get down to 59.3 hertz, which is ERCOT's first level of under-frequency load shedding. However, on a few buses in the east and north of Texas, the frequency declined faster because of the unique configuration of this particular case, and you got a little bit of under-frequency load shedding. And so the whole point of this is that this is a new metric to start to look at how these potential impacts of the location of the inertia is, and not a lot of, this is still kind of exploring this new metric, but I presented it here and the impact that it has on trying to make these synthetic cases as realistic as possible and contrast our responses with or compare our responses with actual good responses in a useful way. So I want to just end with a couple of summarizing thoughts. The main one I want you to take away from this is that our synthetic grids are available for your research, and we do a lot of work to try to validate them, make them useful. So I encourage you to use them, and I encourage you also to give us feedback. These are always ready to be improved, and so the more that you can give us feedback, the better they'll be. So feel free to jot down that website if you need to. These are designed to, in this paper, we're focusing on designing to match wide area inertia adequacy characteristics of real cases. And so we looked at it from a statistical point of view and a performance point of view, and continuing to do that. And then this idea of the locational theoretical Rokoff was a helpful analysis to screen a lot of scenarios quickly and kind of get a sense of what the impacts of where the disturbance is and where the different frequency response resources are, and kind of maybe push the ball forward on trying to understand this topic a little bit better. So that's my presentation.
Brilliant, thank you very much. Do we have any questions? Deepa?
Hey, Deepak from EPRI. Adam, great presentation. When you created those 7,000 scenarios or 20,000 scenarios, in each of the scenarios, was the location of the generation the same and just the inertia was varying around the network? Like say, for example, if I have in one scenario, say the base case has 70 megawatt of generation, of which say 50 megawatt or 60 megawatt is conventional and 10 megawatt is wind. Now, when you go to, let's say, 30 megawatt wind or 40 megawatt wind, and the remaining being conventional, do you retire conventional resources in one area and shift the resources to another area of the system where more wind is coming in?
These are mainly reflecting operational differences, not future scenarios. So one thing to know about the synthetic grids is that the generation is real. It is real, because the generator location, generator capacity, generator fuel type is all public information. So we start with that, and you can see from the very first figure that you have a lot of wind in the west and you have more conventional generation in the east. That was maintained. But as the wind levels change, then we have a unit commitment algorithm that sets up what of the other generators are online and then dispatches them appropriately. And of course, based on the loading and the wind, that will kind of determine what inertia is there and where it is. But we didn't really, we didn't model things like retirement and into the future, but we hope that this metric may be helpful for kind of testing out large numbers of scenarios that would include things like that in the future. So thanks. Yeah.
Cool. Thanks.
Thank you very much. I think we'll move to the discussion part. At which point, I think I'll sit down and I'll hand over.
This is good, right?
Okay, so we are ready to start the panel discussion, and I see already Claudio has lined up for the first question. So Claudio, please.
Claudio Canizares, University of Waterloo. Thank you, Costas. This is a question for the neural network modeling. A couple of years ago, we published a paper in which we were looking at something very similar, but only for batteries. And in that process, we discovered something very similar to what you noticed, which we could predict P reasonably well, but no Q. We use an ARCS neural network, which are good for dynamic modeling. But we could not capture the reactive power scenarios. So what we did is we divided P and Q, two different neural networks, and that captured the phenomenon. So something you might want to consider, that, in other words, not trying to capture everything with one big neural network. For us, didn't quite work, and when we separated, it did work very well.
We have actually tried that, and I think it's really the disturbances that we have been using. I think I have read the paper, and I think it was also using short circuits, because the change that we see in the reactive current is quite little, which is why I think that the prediction is this bad. So for this, I have tried using two neural networks, like one for active and one for reactive, but the performance on the reactive part wasn't getting better.
Well, in our case, improved. I have a question about the first paper, which was the issue of simulation. It was somewhat asked already, simulating the protections. There's a task force in IEEE task force in power system modeling, including protections. And for this type of problem, I guess protections have been shown to be difficult to model and important to model as well, because otherwise you don't capture, as you mentioned yourself, the load shedding, for example, made a big difference, right? So can you comment on how you model the protections in these simulations? Thanks.
Yeah, thank you very much. So the protection is all assumed to be perfect. So we don't model any protection failure, and the protection is essentially so for thermal we do it kind of inverse with the overload, so inverse time with overload, and then we have under frequency where I think we've just modeled essentially the equivalent of the GB system in terms of the various shed levels, but we assume again perfect measurement of frequency, so because we just feed that in. So we don't model anything associated with the measurement process or the actuation process itself in terms of that potentially not working well. There's no noise, there's no signal delays, there's no protection failure. So those elements, if included, would also, I assume, make this a more accurate thing, but it would probably then open up the need to, well, it would open up the need to also then run that probabilistically as well. Because if you have certain probabilities of protection failure, you're going to need to run a large number of samples before you then converge on a reasonable result. So you'd want to run the same contingency many times, and then the computational burden, I think, would become too much.
Okay, thanks. There's another question.
Hi,
Please identify yourself.
Matt Bossart, University of Colorado. My question is also for Johanna. I was wondering, you mentioned you developed these distribution system models to capture uncertainty. Can you talk about the practicalities of integrating those into the transmission level large simulations? Like, is that something you've done or tested?
Yeah, so this is really what I'm currently doing. I have successfully integrated the linear regression one. So is the question really about the technical integration, or then more like?
Both the technical integration, yeah, and the testing of how they perform.
Yeah. So I have done technical integration for linear regression and also for the first neural networks. I haven't really assessed the performance yet because they're initialization problems. And I've also talked with a couple of others about this, and it's a problematic question. So it hasn't been successful yet for the neural networks. Yeah.
Sounds good. Thanks.
Okay, Misha.
Mr. Chertkov, University of Arizona. I actually have two questions. So first of all, well, the story about force versus events-driven well, oscillations, right? Distinguishing between the two. I'm recalling, well, Yulu, she was here, but I don't see her now. Well, a number of years ago, with Scott Beckers, my, well, by then Los Alamos colleague, they developed this green function method, which was meant to be more or less for that type of problem. So I wonder if you're familiar with this approach, and if you try.
Is it for specific?
Well, it was, yeah, it was a talk on force versus events-driven.
Sorry, can you repeat your question?
Green function approach. So it's an approach which was developed by Yulu and Scott Beckers. Well, they had a paper in 2014 or 15, I don't remember. I wonder if you are familiar with this approach, and if you tried.
Not actually, I have not. I'm more than happy to receive more information.
Well, Yulu, well, she is not now. Well, she is attending, right? And but I can point you.
Thank you for
paper. And then a question to last presentation. Well, from Texas A&M, Rokov versus frequency, and so why do you prefer Rokov as opposed to frequency? That's one sub-question, and another. I remember Tom over B, which is obviously behind this Texas A&M story now. He was showing these beautiful movies, right, of how things propagate in various situations. It was demonstration of power vault when I first time saw it, and it's much more informative than just frequency. Well, this movie is informative, in particular because you see that on the boundaries of a grid there is a reflection of this electromechanical wave, and that's actually where it hits the hardest. So I wonder if you're using this technique, visualization, but also analysis.
Now I've been thinking about the second question. What was the first one again?
Rokov or frequency?
First is Rokov versus frequency. So why you prefer Rokov to frequency?
I wouldn't say I prefer one or the other. In fact, in ERCOT, as I understand, they're concerned about where the frequency ends up, not so much the I mean, I'm concerned about the rock-off because I'm concerned about the frequency, and the rock-off tells you hopefully where the frequency is going in the short term.
Yeah, but then question about movie, right? So visualization.
Yeah,
so
the
why didn't you
movies
show
are
us
cool.
that?
I mean, they show you, yeah, they show you you're talking about. There's these animations of the contour of the frequency as a disturbance propagates, and
well, once
we
again,
can
so
make
it's
movies,
informative
yeah.
from my point of view because it shows you where and when after perturbation it hits most. And it's very surprising when you look at it. It's, yeah.
Yeah, I think a lot of that is not super well understood, and the movies do help to show some of those effects. Yeah.
Okay. Please identify yourself, Deepak.
Deepak from APRI. So question for Johanna. So a transmission grid, so let's take the Western Interconnection in the US or North America, has around 6,500 locations of load and substations where load is aggregated. We use a composite load model to represent the entire dynamics of motors, DER, everything. If we have to apply a machine learning based model, do we need to do 6,500 trainings? And where would we get the data to train 6,500 instances of that model?
Yeah, that is actually a very good question. Yes, so it is the question of how detailed do you want to be, and do you want to become more detailed than you currently are, because this is the opportunity to become more detailed than you currently are. The way that we kind of saw this going would be that kind of the distribution grid operator would supply this model, and then this would at the same time also, like, privacy concerns and all of that wouldn't be an issue because it's going to be a black box. But yes, it would require tuning of each of these distribution grid models, which then is very intense. But I mean, it's the question of how much of a benefit are you going to get on your transmission grid simulations, and then if you think that in the future, so for example, for the Swiss system, I know that in some time instance, there's 60% of the generation coming from distribution grids, which means that they will also need to supply most of the ancillary services. So if they are coming from there, we kind of need to integrate them in the system in a better way. So this was a first approach at doing that. I know that it is a very computationally intense approach as well, but it is less costly than modeling them with full detail.
Yeah, thanks. So one follow-up question on that. You mentioned about...
Rodrigo has to point out something and then you continue.
I would like to make a comment on your question, Deepak. I don't... The way we are seeing it is not that we need a model for each distribution feeder of the whole network. But the TSOs are starting to identify situations in which the models affect the dynamic behavior of the transmission system. And those specific locations need better models. So you may continue using a very simplified model where the distribution system does not impact as much, but you can use this approach to get a better model, just to get a better representation of the dynamics of the distribution grid at the locations where you found that your simulation results of the transmission system do not match what happened in reality.
Okay, yeah, thanks, Rodrigo. So just to give a little bit background from the Western interconnect that we have, every distribution network is modeled by a dynamic model in the base case today. And the dynamic model contains three-phase induction motors, one single-phase induction motor, DER, static load, power electronic load, all of it. So there is a dynamic model that we use. So now a follow-up question regarding how much detailed can we go, and this is as you mentioned, this may be the time to go towards more detail. Have you thought about carrying out a study comparing from a transmission system perspective? If I use, I think on your slide you called it a gray box model on the left-hand side of the first or second slide. So if you use a gray box model which has the dynamics represented of these various elements, and you use a model from the machine learning perspective. From a transmission system perspective, now if you run a planning study to understand how the impact would be of the distribution system, do you get instances where your decision that you make on your planning system or transmission system will change? So supposing I use the machine learning model on the transmission system, and I use the gray box model. Will I have a scenario, or have you seen or come across a scenario where if I'm a transmission planner, I will need to change my decision of what I do?
Wow. Yeah, I think that it's also a very good question. As I said, I have not implemented it yet in a transmission system, and my goal is also to look into like comparing different approaches and seeing what works well, what doesn't, and if there exist those specific cases. I can just maybe pose a guess there. That would be that if you have a system where, for example, you also have demand response and exercise that, like really if you have a system where from a specific area there is coming a lot of quite some response, then you would need to model that in some way. And what we have seen in our studies also, actually this is in another project, but what we have also seen is really that there is this interconnection. I think we've also been talking about that between active and reactive power, and that you cannot just make like the decomposition like we have usually done. So you also need to incorporate that in the modeling, which then would be taken care of here as well. So yes, it's an open question, and it's one that we also have in mind.
Thank you.
Okay.
If you
yes,
allow
please.
me a follow-up again. We are working on this topic because we have indeed seen a situation in which this is needed. What happened is that in Brazil, there is an export of load. In one part of the year, there's an export of power from the northeast to the southeast, and the southeast is the main load center. And then perturbation occurred, and what the TSO model predicted for the first stage of load shedding was that the load was supposed to go below a certain level that would render the system safe. And then what we discovered, what the actual data showed that the load as seen from the transmission system actually increased. And what was the reason for that? The tripping of distributed energy resources, because the protection is much more sensitive. So then if you lose more distributed generation than you shed load, it becomes clear that you need this better modeling. In this specific area, you need better modeling. Maybe not for other ones, but in this case, you do need it.
And the TSO already had a dynamic model, or they didn't? Oh, sorry, Kostas,
we have two other questions and limited time, so you can take it offline. Ian.
Ian Hiskins, University of Michigan. I was actually going to make a comment that it was exactly what Rodrigo said. It's one thing to model 6,500 loads in the WEC system or in the Western Interconnect, but how many of them actually need to be modeled? How many of them actually impact on system behavior? And the other thing is how many of them, if you take the model, if you choose a model that corresponds to 3 p.m., it's going to be vastly different to the behavior at 7 p.m. And so now you have to have different models for different times of the day, and WEC isn't doing that. But on the subject of load modeling, one of the really interesting things that we've noted with electric vehicles, which presumably will become a larger part of the load, and probably other things as well. There's a threshold where they just cut out the charges below, somewhere around about 0.7 per unit voltage, maybe 0.8. But higher than that, their normal load, below that, they're gone. And that threshold can make a huge difference if you're dealing with large electric vehicle load that suddenly, for one disturbance that goes to, say, 0.85, you get no change. For a different disturbance that takes the voltage down to 0.8, you lose a massive amount of load. And that sensitivity is going to become really significant with growth in things like electric vehicles.
Okay, somebody wants to respond? No, if not, last question by Panos.
Panos Papadopoulos from the University of Strathclyde. So probably touching a little bit on what Ian was saying. So about the active distribution network modeling, if I understand correctly, you looked into the variation only of the control parameters, right? Or physical parameters, let's say motor variables and so on, but not the operating parameters of the active distribution network. Is that right?
Yes, so we have changed, so the size of the loads changes, at least for the thermal part it changes. So we are assuming we know we know how much load consumption we have, but we change the shares between the 3 different types that we have, and then all the control parameters, but we assume that they are following a grid code that is exact, so we haven't changed the grid code. Mm-hmm. We also assume that we know all of the line parameters and everything accurately.
I was mostly talking about the, let's say, size of the power output of the converter, for example, which can vary between the day. It could be, but this is solar PV that now it's midday and it's there, but then at night it doesn't, or wind might be there or not, or EVs might be there or not. So did you account for this variation, let's say?
Not yet, because that would mean that it is a bit like a different operation point. So all the inverters, they are operating at the same operation point so far, but this is also something that I'm actually doing also now.
Okay, perfect, yeah. And maybe just a final note there on that. So I think it's important also that you're probably doing that as well, to quantify also the impact of the variation that you saw from ID, IQ on, let's say, transmission level system metrics, for example, frequency nadir or the critical clearing time, or because I have the feeling that we probably will see locations where it's much more important to have the ADN very well represented because it affects a nearby generator, for example. So yeah, just a comment mostly on that, and maybe if you had any views from your own studies with respect to that.
Yeah, it's actually exactly what I presented at PSCC.
Right.
So, and it's out there.
Okay, thank you.
Okay, so if there is no other question, thank you all, and thank all the presenters and the contributors.